Now, there exists, in fact, another representation of Green's function, which is going to be quite useful. Let us discuss that. So let me draw a line again here. So another representation for Green's function so show that for harmonic oscillator, delta t minus t prime is same as limit epsilon going to 0 minus h bar integral dE over 2 pi minus infinity to plus infinity e to the power minus I e delta t divided by p square minus omega square plus I epsilon. I'm sure you are familiar with this. You have done it in course quantum field theory 1, and show that for Klein-Gordon field, delta x minus y can be written as epsilon, limit epsilon goes to 0, h bar times ddp over 2 pi to the power d minus infinity to plus infinity e to the power I p dot x minus y divided by p square plus m square minus I epsilon. This difference in the sign is nothing but there's an overall sign difference as well. So actually the signs are same here. P square, P0 square will have a negative sign here. And then P square, P vector square plus M square will have a positive sign. So if you take this minus sign out, it will match the result exactly with this, with omega square given by being given by omega p square, which is p vector square plus m square. Now there exists Euclidean version. So this is actually when we discuss this wild fluctuation of the phase, path integral phase, and the cure, one of the cure was the I epsilon prescription. It is in this prescription. You can also have a Euclidean version. If you do Euclideanization, then Euclidean version is given by, so define Euclidean Green's function x bar minus y bar, which is by definition is same as delta x minus y, with x0 is minus I x bar 0, and xi is same as x bar I, and so on for the y also. Okay, so you take the same and then do this analytic continuation, then show that this Euclidean Green's function will be given by I h bar integral d d p bar by 2 pi to the power d minus infinity to plus infinity e to the power e to the power I p bar dot x bar minus x bar prime divided by p bar square plus m square, and you don't need any I epsilon. Here, a bar dot b bar is the Euclidean dot product, which means a0, a bar 0, b bar 0 plus a bar I, b bar I. So now let's ask this question: how to show physical equivalence of physical equivalence of relativistic quantum mechanics free and Klein-Gordon. If you have not already guessed how that can be done, let me go in steps. So recall that non-relativistic worldline propagator causal or retarded propagator was shown to be Green's function for Schrodinger equation, that is I h bar del t minus h k retarded xt y t0 was equal to I by h bar delta x minus y delta t minus t0. So you could ask the question, that was the non-relativistic worldline propagator using path integral. We calculated using path integral. Yeah, this is nothing but that x comma t, y comma t0 retarded. So the natural question whether is the relativistic worldline propagator also Green's function for some equation. What is that equation, if it is? So recall the result. We wrote down the result here. We're referring to this. Whether this is a Green's function of some equation. So this is nothing but k xf minus xi, which is xf So we will show that k x minus y is Green's function of Klein-Gordon equation, which means k x minus y is up to a phase same as delta x minus 1. Okay, and that we will consider two methods. We'll discuss two methods. One is interpretation. An interpretation from the QFT side to argue that this must be the case, and the other one is explicit calculation. So let me first begin with interpretation. In QFT. Okay. So in QFT, so since the quantity here is the overlap between xf and xi, if you want to construct this directly in the QFT, we should be able to find what the single particle excitation is, right? So single particle, how to construct single particle state in position space. So the question is, so then therefore we need to identify single particle state in position space. In Klein-Gordon theory, and then show that delta x minus y is up to a phase x-y overlap. Okay, so to do that, let us first consider vacuum. Vacuum is the one which is annihilated by all the A P operators for all P. Then single particle momentum eigenstate is P is equal to root over of twice omega P AP dagger. So let us define this, and then from there you calculate the overlap between two momentum eigenstates, and that will give you 2 omega p times 2 omega q square 2 omega q vacuum expectation value of AP AQ dagger, and that is same as 2 omega p delta p minus q. Now, why to construct consider the single particle momentum eigenstate? Why does one keep this square root 2 omega p factor? The reason is that this inner product is supposed to be proportional to delta of p minus q vector, which is not a Lorentz invariant quantity. It is this normalization that gives this 2 omega p factor, and this entire thing is Lorentz invariant. So this is an aside. And show that under a Lorentz transformation, p going to p prime, p vector q vector goes to p prime vector q prime vector, and that is same as pq. In other words, omega p delta p minus q is equal to omega p prime delta p prime minus q prime. You can see for example Peskin and Schroeder. There's a discussion on this. Okay. Now, then calculate phi hat x acting on vacuum, and this will be given by integral dnp over 2 pi to the power n by 2 1 over 2 omega p e to the minus I p dot x p so at x0 is equal to 0 time, this is 0x vector acting on vacuum is integral dnp over 2 pi to the power n by 2 1 over 2 omega p e to the power minus I p dot x acting on p. Okay, this of course looks like eigenstate, position eigenstate x vector in non-relativistic quantum mechanics, except that this factor is unusual. This unusual factor is present because this state is unusual. If this state is defined, the state itself is defined with this factor, and what one should actually look at is the inner product. One should calculate. One should look at the inner product instead of this state. One should look at the inner product with a momentum 0 x 0, and that is 1 over 2 pi n by 2 e to the power minus I q dot x, which is what we know already. I mean, which is what is expected. Okay,